Exercise 5C2, I'm going to do question 1, which should be fairly straightforward because it's the first one. The velocity is 1 minus 2t centimeters per second. We have to find distance and displacement after 1 second. 1 minus 2t, all right? So v of t. So it's a pretty straightforward velocity function. What I mean by that is I can get a picture of this fairly easily, of this graph, right? So I've got velocity, centimeters per second, isn't it? Times in seconds. Velocities in centimeters per second. Y-intercept is 1. We've got negative downhill gradient here. The x-intercept, so we could say when's the velocity equals 0? When 1 minus 2t equals 0. So t would have to be a half. We'd have 2t equals 1, meaning t is a half. That's our x-intercept on the graph. I wish I'd drawn this a bit bigger now. I'll put it maybe in here. We've got this line. So there's no negative time. I can just start here and go down with my negative gradient. That's at 1/2. Right? If they're saying what's the velocity at 1 second, I might be able to change colour. Go orange. Yeah, try that. They mean, what's this area? Can't remember what I said now. Did I say displacement or? They want displacement and distance after 1 second. So 1 second is about here, let's say. 1 second. Area under the curve would be there. And here, right? Now, this is a straight line, and the x-intercept's exactly halfway between the 0 and the 1. These are going to cancel out because those two triangles will be the same size. This one looks a bit bigger, but it's because I haven't drawn very well. So displacement's going to be 0, it looks like, because that triangle should be the same as that triangle. I could work this out without any calculus because I've just got triangles. I could say, what's the area that's a half, that's 1, area equals a half times the base length, which is also a half, times the height. So the area is a quarter. So that area is a quarter, that area is a quarter. It means we'll be minus a quarter, right? Maybe we just check, is that height really 1 there? We could get the height from our velocity functions. We say, what's the velocity when the time is 1? We'd be doing 1 minus 2 times 1 is minus 1. So this point in here, time is 1, but velocity is minus 1, right? So that height of that triangle is also 1. It's the same triangle, just upside down, right? 1, and then this length in here is also a half. So I already know the answer. The distance versus displacement, right? The displacement is 0 because it's coming from a quarter plus minus a quarter equals 0 centimeters. But the distance is a quarter plus a quarter equals half a centimeter, right? Because distance, I don't care if I have negative velocity. So this might be going forward here or going to the right of the origin. And then this part from t equals a half to 1, that's going backwards or going left. And you're getting back to where you started if you thought about your motion diagram. So your motion is going to the right, turning the corner, and coming back again this way. So this is 0, this is at a half, a quarter. Motion is graphing position. So we're saying we're looking at position or at the centimeters. So you went you went a quarter centimeters and you came back a quarter centimeters, right? Which is what I've got in my numbers here. So that's done. Let's now check it out with the calculus. I don't know why this won't show on the other screen, but I'm gonna, whoa, don't want to erase everything. Need a bigger eraser. It would be important for us to realize that the velocity does change. So imagine I didn't have the graph. I would need to still think about when does the velocity equal 0? Because that's when you're going to be changing directions. You know, we've already worked this out when t is a half. So we could draw our sign diagram for velocity. Right. Time, this is a sign diagram for velocity, and we've got positive velocities until we get to a half, then we've got negative. You could check it in the equation, like if I put a quarter in here, I'm going to get 1 minus 2 quarters, which is a positive value. And then as soon as I go bigger than a half, like let's make it 100, 1 minus 200 is definitely negative, right? So you need to be recognizing that you're changing velocities, so that if you're working out distance from calculus, you could be doing this. You could be saying, well, I want the integral up to a half. I'm going to figure that out. I want the integral of the velocity function. Let's write out the actual function. And I'm also going to need the integral from a half up to 1. Now this second integral will come out negative, but for distance I don't. All my negative answers will become positive because, you know, distance doesn't have the directional component. It's like area. I just want to know what the area is. So here you'd have t minus 2t squared divided 2, which is just t squared. And you want to evaluate that from 0 to a half. And here you would have the same antiderivative, and you want to evaluate from a half to 1. So this over here, you're going to get a half minus a half squared, which is a quarter. All right, so that's what's happening when I plug my halves in. This is fundamental theorem of calculus. Minus 0, because the t's will be 0, and you get a quarter. Over here, you'll get, we've got to put ones and halves in. So we're getting 1 minus 1, because 1 squared is 1, minus the same one we've already done up here. So it'll be half minus 1 half squared. A half times a half, that's a quarter. And you get minus a quarter, right? So again, your displacement will be 0 because you'll have a quarter plus minus a quarter. As in, if I'm going from 0 to 1, dt, I get 0. That's displacement. I'll just write that here, displacement. But distance is a quarter, and then I make that one positive, right? So I'll say the distance equals a quarter plus a quarter equals a half. So that's doing it from calculus where there's no graphing needed, and without the triangles. But hopefully that ties everything together nicely for you. All right, so that was question 1. I'll stop the video.